Okay, so it's pulled back a distance of 2.2 meters by an unknown force. Okay, the rock has a mass of 110 kilograms. Okay, and reaches a speed of 22.8 meters per second. Would that be VI or VF? VF. What would VI be?
0.
Yeah, okay, we have to get that kind of from the context of the question. A loaded catapult isn't moving, okay, so the initial speed would be 0 meters per second. Okay, so how much force was used? All right, well, obviously we're going to be changing the mechanical energy of the rock, specifically the kinetic energy of the rock, okay, because it doesn't mention anything about the rock traveling vertically, even though obviously with a catapult that's what it would do. All right, so we're going to say then that the force times the distance equals EK final minus EK initial. What's EK initial? 0. It's sitting in the catapult. At that point, it would actually have elastic potential energy due to the nature of the catapult. All right, so now we can say force times distance equals 1/2 mvf squared, and solve for F, because that's what they wanted to know. Okay, so we would go 1/2 times 110 times 22.8 squared divided by 2.2. Okay, and if we do all of that, it's what?
570.
570 newtons? Okay. Okay, that would be the force. Everybody all right with that? Yes?
Would you mark us differently if we use like VF equals VI plus 280?
And then you solved for acceleration?
Yeah.
And then you went mass times acceleration?
Yeah.
Nope. Be perfectly valid. Yeah. That would be solving it as a Newton's second law problem, but equally valid to do it that way. Yeah. Okay.
Pretty sure it's not 570 newtons.
All right, let's punch it in.
What did my calculator mean?
0.5 times 110. I know my method's right. Times 22.8 squared divided by 2.2. Yeah, a lot bigger. 13,000. 1.3 times 10 to the 4, because we only have 2 significant. No, we have 3 significant. 2. So 1.3 times 10 to the 4. Okay, no worries. It happens. I think I forgot to square it. Yeah.
That's fine.
Okay. Questions on that one? Okay, again, the one I put on your test, not a whole lot tougher than that, really. Okay. Okay. For our second one, this is a law of conservation of energy question. Okay, so we have our roller coaster, like this. Okay, and it is 12 meters off the ground. Whoop, I drew that backwards. Never seen a roller coaster that goes like that. There must be part of it we're missing over here that would be much higher. Okay, so a 350 kilogram roller coaster is 12 meters off the ground. Okay, moving at 31 meters per second. Okay, and we want to find out how fast is it going here when it is 22 meters above the ground. Okay. It doesn't mention anything about friction, so what do we have to assume here? That it is frictionless, and as a result of that, our initial energy and our final energy are equal. Okay, and that no work is done against non-conservative forces. Okay, are any of those 0?
No.
No. Okay, there's a value for each and every one of those. All right, that means that I can expand it out. Actually, before I expand it out, I'm looking for VF, which would be part of this term right here. So what should I do with EPF right now?
Subtract.
Subtract it over to the other side. Okay. Here, can you put that down? Thank you. Okay, so what we're looking at now is the point where we can put in our formulas. So we'll have 1/2 MVF squared, or sorry, MVI squared. Oh, come on. MVI squared plus MGHI minus MGHF equals 1/2 MVF squared. All right, what's in every term?
Mass.
Mass. So I don't need the 350. It's going to cancel. All right, I just need to divide both sides by 1/2 and square root. I mean, have we done a ton that work out exactly the same way? You're either solving for a height or you're solving for a speed in these questions. Okay. All right, so once we have that, okay, if we plug in our numbers here, we should have 1/2 times 31 squared plus 9.81 times 12 minus 9.81 times 22 divided by 1/2, all square rooted. So 0.5 times 31 squared plus 9.81 times 12 minus 9.81 times 22 divided by 1/2, square rooted, 28 meters per second. Seems fast, but that's what it comes up to. Okay, didn't slow down much, but it's frictionless, so it wouldn't. Friction is usually what slows things down. So. Okay, questions there? All right, should you expect something like that?
Yes.
Okay, now the other day, okay, we talked about this, but I just want to quickly review it. If I've got a helicopter and a plane, and they're both at the same altitude, okay? The helicopter drops, let's say, a 50-kilogram object towards the ground, and the plane, which is moving horizontally, drops an identical 50-kilogram object. Which one of those objects has more mechanical energy? The one from the airplane. Why?
Because it's like moving forward and down.
Right. It's got kinetic energy that the one drop from the helicopter does not have. The one drop from the helicopter isn't moving at time 0, the instant it's dropped, whereas the one that's moving in the plane, or that is in the plane, sorry, is moving. Okay? Even though it's moving horizontally, it still means it's got kinetic energy because energy is scalar. Okay? That making sense? You know, just in case something like that comes up on your test. Maybe? Yeah. Okay, so any other questions on Unit 2 before we move on to Unit 3?
So can I make the motion?
Yes.
Good question. Thank you.
All right. So, need you to find Unit 3, Lesson 1 on uniform circular motion.
Oh, is that very nice?
Yes, it is. It's the far side.
I read that stuff all the time.
Stay on.
Because they'd have a button like that on your seat, yeah. Okay, so what we're going to go over today are kind of the basic principles of what we call uniform circular motion, okay? And as I am always concerned with saving the taxpayer money, my pendulum can also double as a circular motion demonstration. costs taxpayer nothing, okay? It's the drawstring from my hoodie and a roll of tape from my house. I'm so generous. No. Okay, so if something's moving around and around in a circle, okay, at a constant speed, why is it doing that? Like for circular motion to happen, circular motion is not something that happens on its own. Moving in a straight line can happen on its own, but moving in a circle can't. What keeps this thing going at a constant speed, but in a circle instead of a straight line?
Like the string keeps pulling it like back.
Yeah, the string keeps pulling it, actually where? You said back, but even more
Like towards your hand.
towards the center of the circle. Okay, so if the string is always pulling towards the center of the circle, it's exerting a what?
Force.
Force. Okay, so I said this thing was moving at a constant speed. Is it moving at a constant velocity? No, it isn't. Okay, what is it always doing?
Going back.
Changing direction. Okay, so it's always accelerating, even though the magnitude of its velocity doesn't change. The direction of it does. Okay, if it's always changing direction, then its velocity is changing, and that means it's always starts with a accelerating, and it's accelerating because of the string, the force that's pulling it back towards the center. So circular motion of any kind doesn't occur unless there is something pulling towards the center. Okay? I mean, think of the Earth orbiting the sun. What keeps us in orbit around the sun? Gravity. Gravity's always pulling us towards the center of the sun. Okay? Fortunately, the Earth moves fast enough that we don't get any closer to the sun or further away. Either one would be equally disastrous. Okay? But it's always exerting a force and causing the Earth to accelerate. Okay? Not actually make the Earth go faster, although that actually does happen in its orbit. There are parts of its orbit where it moves faster than others. Okay? But it is always changing the direction of the Earth. Okay? Earth does the same thing to the moon. Okay? It's always accelerating the moon towards its center, okay? Making it go in a circle. Okay? Everybody okay with that idea? All right. So this is very applicable to the driving conditions for the past week or so. Okay? When we all saw what happened, okay? The first day it got all snowy. Somebody tried to take the corner out there. Okay? They wanted to go in an arc, which is part of a circle. But there wasn't sufficient what? Force. Yeah, which force? Friction. Yeah, there wasn't sufficient friction. Okay? There wasn't enough friction to make him go in a circle of the radius he desired. He did travel in an arc. That arc just ended in the pond. It didn't end in where on the road, okay? Because there wasn't enough friction to support that particular circle. Right? So the amount of force pulling back towards the center is what determines the radius of the circle that you can travel in. Okay? The more friction there is, the tighter the circle you can travel. The less friction, the more like a straight line that circle becomes. Okay? And then you encounter things like lampposts, ponds, other cars, okay? Undesirable things. Okay? So it's something to keep in mind. Friction acts as a centripetal force. Okay? Now, you're probably thinking I said that wrong, and that's okay. You're wrong. I said it right. Okay? I said centripetal. Okay? You're probably thinking I should be saying centrifugal. Okay? That's different. Right? Centrifugal looks like that. And they are actually the opposite of each other. Centripetal means center seeking. Centrifugal or centrifugal means center fleeing. Okay? There's actually no such thing as a centrifugal force. Okay? We use that term all the time incorrectly. Okay? If I leave a circle, it's because of a lack of a centripetal force, not because of a centrifugal force that is throwing me out of the circle. Okay? What makes me leave the circle is Newton's first law, inertia. Okay? It's inertia that plasters your face up against the window of your friend's car because he took a corner too fast in good driving conditions. Okay? All right? Or he's taking the corner really fast and you're grabbing onto the holy crap bar there on the panel, okay, or on the C-pillar there, and you're holding on for dear life, okay? Because your inertia wants you to go in a straight line that would leave the circle, okay? Some centripetal force, the window, okay, or whatever, okay, is keeping you in the circle, or your seatbelt, okay? This is why the idea of having a Jeep with no doors on it is really bad, okay? I mean, yes, you should be wearing your seatbelt, but, you know, if you're even beyond stupid and not wearing your seatbelt and in a Jeep with no doors, okay, and someone takes a corner and you're on the outside of that corner, you will obey Newton's first law. You will travel in a straight line exiting the vehicle. Okay, not good. You don't want that. Okay, so it's something to think about. There is actually no such thing as centrifugal force. There's inertia. It can feel like a force, okay, but it's not actually a force. It is just the tendency of an object to continue going in a straight line. Okay? It requires a centripetal force to make something actually go in a circle. So I'm going to show you. Okay, so if we're going to move in a circle, then we need to have something that is going to keep us in that circle, something that is going to apply a centripetal force that's going to keep us accelerating towards the center so that we go around and around. Okay, if we don't have that, then we just obey Newton's first law like the morons on merry-go-rounds with motorcycles, off they go. Okay?
All
right.
It's something my dad did as a kid.
So if something's going to move with uniform circular motion, that is move in a circle at a constant speed, okay, obviously not a constant velocity, okay, then we've got to have that force that's pulling. It's going to be not a constant velocity because the velocity's vector is always changing, okay, and any change in velocity, even if it's just the vector and not the magnitude, still counts as an acceleration and still requires a force, okay. So this is still a little bit of Newton's second law. Okay, we still have Newton's second law being applied here. There's a mass that's accelerating, okay, but its acceleration has to be towards the center. Okay. Now, some terms that are going to be new here. If I want to calculate the speed that something is moving around a circle with, or the centripetal velocity, okay, of the object, I would use V equals d over t. Okay? But now we're talking about a circle. So what's the distance called around a circle?
The circumference.
The circumference. How do I calculate that? Right? Pi times diameter, or pi times twice the radius, so 2 pi r. Okay? That would calculate the circumference of the circle, which would be the distance that we would travel. Okay? Now, the time is actually written as capital T in this formula, not as little t. Okay? The reason for that is this is a specific time called the period. Okay? And the period is the time for one cycle, or one circle in this case. Okay? So Earth's orbital period is 365.25 days. Okay? Nobody looked at me strangely when I said that. That's good. We recognize that it's not 365 days, right? That's why we have a leap year every 4 years, because it's 365.249 something. Okay, so it's 365 and a quarter. That's the Earth's orbital period. The moon's orbital period is like 28 point something days. Okay, period is the time for one cycle, circle, orbit, whatever. That's what period stands for, and it is always abbreviated capital T. All right, so if I want to calculate the speed that something moves in a circle, I take the circumference of that circle, I divide it by the time for one cycle of the circle, and I'm off. Okay, now, period is measured in seconds per cycle. Sometimes we use the inverse of this, okay, and we use cycles per second. also known as frequency or hertz. Okay? Now, we most often associate hertz with sound. Okay, the frequency of a sound. So if you're in band, okay, certain notes have certain frequencies. Those frequencies also have certain periods, but we never measure them as 0.005 seconds or whatever it happens to be. It makes more sense to say this number of oscillations per second. It basically means if you were, let's say, playing a note on the saxophone, how many times the reed would vibrate up and down in 1 second. Okay? That would be the frequency of the sound you would produce. If you've got a stereo, like the guy that lives near me, I don't know what his name is, I call him the guy, okay? Because that's what he does every time he goes by my house, okay? So he's got a bunch of subs in the back of his car, clearly, okay? And the frequency at which the subs do this is like probably 60 hertz, okay, or something like that. It's slow enough that you could actually see them moving back and forth. Okay? If you ever watch a subwoofer, you can actually, it moves slow enough that you can actually detect it. Okay? So typically we use hertz when we're talking about cycles per second. Okay? It is the inverse of period. So if I had this formula here, okay, and frequency is the inverse of period, how could I write that formula to include frequency instead of period?
T divided by 2 pi r.
Nope, so I don't have t in there. How would I substitute f in?
2 pi rf.
2 pi rf. Okay? Because really, what this formula is saying is 2 pi r times 1 over t. Right? Really, that's what that formula is saying. Well, is 1 over t f? If I'm dividing by 1, and the other thing is the inverse of that, then I would multiply by its inverse. Okay, so if f is the inverse of t, and I'm dividing by t, I would multiply by f, because it's the opposite. Everybody okay with that? All right, so this formula is on your formula sheet. This one is not. Okay, but it's expected that you could perform that mathematical operation to get it. Okay, so we're going to look at a simple kind of problem here to do with period and frequency. Okay? And it's for something that we've probably all done recently, and that is put our winter tires on. Okay, so when you get tires put on a rim, they have to be balanced. All right? And it has to do with circular motion. If you don't balance them, they're going to vibrate. Okay? And the reason for that is the way that tires are formed is basically liquid rubber is poured into a mold and then cooled. Okay? And then the mold is pulled away, and boom, there's your tire. The problem with that process is it doesn't always distribute the rubber perfectly equally all the way around. So you get heavier spots on different parts of the tire. Okay? Even your metal rim that the tire goes on may have imperfections in it that make one part of it a little heavier than the others. Okay? Well, because mass affects your inertia, if one part of the wheel or tire is heavier, it's going to want to leave the circle more than other parts of the tire. So when you get up to speed, suddenly the car starts to vibrate. Okay? Anyone ever been in a car that's like that? And it vibrates at like certain speeds. At certain speeds you don't notice it, but at like 80, and then again at 100, and then again at 120, okay, you get this vibration. Right? That means one of the tires or wheels isn't balanced properly. All you have to do is take it in, they'll put it on this machine and whirl it around, and it's spring-loaded. So they can detect where the tire or wheel is heavier and put weights on the other side to offset it. Hence, balancing your tire. Okay? Everyone follow me on that? So it's important. If your car does that, you need to take it in and get it fixed. It's really bad for the drivetrain and suspension, and it's not safe to be driving a car where you're down the road. Okay, like it's not safe. Okay. Yes.
Good gadget, bro.
Okay, so here's what we know in this question. We know the radius of the tire is 0.29 meters. Okay? And we know that it's being rotated at 830 revolutions per minute, or cycles per minute. Did they give me frequency or period? Frequency, because it's cycles per time interval. Okay, so they gave me F, but they gave it in per minute. Do I probably want it in minutes? Probably want it in? Okay, will the number be bigger or smaller? Smaller, yeah. This is how many times it goes around in a minute. The times it would go around in a second would be considerably smaller. Okay, how would I figure out how many times it would go around in a second? Divided by 60. All right, so I'm going to get my frequency in hertz, or rotations per second, by taking that 830 and dividing by 60. All right, so 13.83. All right, so I know the radius, I know the frequency, and I'm supposed to find the speed. And I know that V equals 2 pi r times F. Okay, so all I have to do then is multiply these numbers together. Now, when you do this, should you use 3.14 or the pi function on your calculator? The pi function on your calculator, please and thank you. All right, so 2 times pi times that number there times 0.29. All right, so that's 25.2 meters per second is how quickly that's moving. Divided times 3.6. So that's 91 kilometers an hour. Okay, that tire would spin at on the machine. They do have to get it up to a certain speed in order to detect those vibrations. They're not going to probably detect them at 20 kilometers an hour or 30 kilometers an hour. Okay, so they do crank it right up. Okay, is that a fairly straightforward formula to use? I mean, really, it's V equals d over t applied to a circle. And really all it is. Okay. Questions so far? All right, so I just did that. Okay, so the definition of uniform circular motion emphasizes that the magnitude of the velocity is constant, but the vector is always changing. Okay, and as we said earlier, if the force that's holding this thing in the circle disappears, I'm going to try not to hit anybody when I demonstrate this. Okay, all right, so I've got it moving around and around the circle. Okay, if I let it go,
Good job, Clarice.
okay, it's stuck in just where it's going to go. Sorry. It didn't hit you. All right, so did it fly in a straight line after that? Yes. Okay, and I saw where that straight line was going to go after that moment. I tried to snatch it, but I missed. Okay. So yeah, that's what it's going to do. Once that force is gone, then it obeys Newton's first law. Okay, just goes off in a straight line. Okay. At least you weren't here the day I tried to demonstrate the vertical one with the bucket of water, and the handle broke. Okay. Where's the handle going to break? At the bottom. Exactly. So I'm whipping that thing around. Right here, the handle breaks. Like against the wall, splash everywhere.
Better than the top.
Well, but it won't break at the top, right? Because there's actually less strain on the handle at the top. The strain is greatest on the bottom. That's where the handle always breaks. Okay, is at the bottom.
Because force and gravity.
Yeah, gravity's pulling down as well. Yeah. Okay. All right, so if there's going to be a change in velocity, then that means that there's an acceleration. Okay, in this case, a centripetal acceleration because it's directed where? Towards the center. For something to move in a circle, it has to be accelerating towards the center. Anything that's center seeking is centripetal. Okay. So, centripetal acceleration is calculated by taking the speed of the object squared and dividing it by the radius. Okay? So, what happens to your acceleration as you increase in speed, according to this formula?
It increases.
It increases in what way?
Exponentially.
exponentially. Okay, that's something we need to think about. Right? So if I'm whirling this thing around at this speed, I don't have to hold on to this very tightly. It's not going anywhere. Now I gotta hold on tight because it wants to go. Okay, I have to exert exponentially more force as I increase the speed in order to keep it in the circle. Something that you might forget until you're, looking at the pond through your windshield, right? Because you were going too fast and you required exponentially more friction to stay on the road and didn't have it, okay? And so, yeah, off you went. Think about that when you're doing the on-ramp over here, okay? Getting onto Highway 2, right? The speed limit on that thing is what, 60? That's terrible, I don't even know what it is. Drive it all the time, I don't even know what it is. Okay, if it's 60 and I try and take it at 120, is it possible that I could do it?
Yeah.
Yeah.
You could. If you have the right vehicle and the right conditions. Don't do it in a cargo van, okay? Because it'll just roll, okay? Don't do it in icy conditions. In fact, yeah, don't go more than 60 under icy conditions. Also, don't go less than 60 under icy conditions. We'll talk about bank curves another day, but that curve is banked like this. If you go less than 60 and it's really icy, you'll slide in. Yeah, okay. There's a real balance point that's set up on bank curves that actually makes them safe. Okay, but I've seen people who were overcautious end up in the middle. And that's really bad if you're behind them. Because you're like, crap, speed up, speed up. We're both going to end up in the middle if you're not going to speed up. Okay, so it is something to think about. Now, what happens with radius? If I'm going in this circle, my acceleration would be a certain value. If I go in this circle, how does my acceleration compare?
When it's
It
slow
would be
down.
greater. Or no, it would be small.
It would be
Your
smaller.
radius is bigger.
Because my radius would be bigger. Okay? This is why you see, like, on racetracks, people try and take the corners as wide as they can. They start out really, like, close, and then they get way out on the outside, because the greater the radius, the less the centripetal acceleration, and the less friction is required to keep them in. If you try and take that a little tighter, or too tight, out you go, because your radius is too small, your acceleration is too great, okay? And the force of friction can't provide sufficient friction to hold you in the corner. Okay, everybody all right with that idea? Okay. All right, so as long as we understand that, okay, that relationship, we're good. Centripetal acceleration is dependent on speed, exponentially, and radius, inversely. Okay, so you take a corner wider, okay, and there will be less centripetal acceleration. Okay. So centripetal acceleration is a vector quantity, but because it's centripetal, its vector is always where? Always towards the center. Okay, so there aren't a lot of times where we actually ask for a vector. If we say calculate the centripetal force, we don't usually require a vector because it's kind of a given when it says calculate something centripetal. It's towards the center. That's what centripetal means. But occasionally, you do get a problem where it says calculate the magnitude and direction of the centripetal force. Well, that's a gimme. Okay, it's always going to be towards the center. Just don't forget to write it if it specifically asks for it. All right, so we want to go, if we want to go in a circle, okay, that's a balance that's achieved between Newton's first law and our desire to go in a straight line and the centripetal force that is accelerating us towards the center. Okay, so when we see something like the moon orbiting the Earth, okay, it's a balance between the moon's desire to fly off in a straight line and the fact that it's accelerating towards the Earth. Okay? The moon is actually always accelerating towards the Earth. It's just going fast enough that it doesn't get any closer. Okay? This is how all satellite motion works. Okay? On the International Space Station, are you weightless or apparently weightless?
Apparently.
You're apparently weightless. You still have weight. You're still attracted to the Earth. Okay? But you're moving fast enough that the distance you fall towards the Earth is accounted for by the distance the Earth curves away from you. So you never get closer to the Earth, even though you're always accelerating towards it. And that's why you feel weightless. You're technically always falling when you're on the International Space Station. And when people first get there, for the first few days, it takes them a while to adapt to that. And people are often violently ill, okay, for the first few days because they have this sensation of always falling. You know that dream you wake up from? You were falling? That's what it feels like all the time, okay, until your brain gets used to it, okay, and actually then kind of shuts off the balance center of the inner ear. Okay? Because when you go into space, the balance center that's in your inner ear is like that car alarm that's always going off for no reason and screaming, and you eventually just tune it out. Okay? Eventually that's what the brain does. It's like, shut up, I'm so tired of hearing you scream about us falling. We're not falling! Okay? And then it just stops listening to it. Okay? That's good and bad. When you get back to Earth, your brain has to shift back to using your ear because now gravity works and your inner ear balance center will work. Okay, but it's gotten used to using your eyes instead. You should see astronauts when they return to gravity. If they've been in zero gravity for a very long time, they are so clumsy. Okay, they can walk just fine as long as they're looking straight ahead. Okay, if they're walking and somebody says, "Hey, Chris," and they're like, "Yeah," they'll do this. "Yeah," and they'll just turn. They don't mean to turn, but their brain has become dependent on their eyes to tell them which way is right in terms of their balance. If they look up, they'll fall over. Okay? If they look to the side, they'll fall. Okay? Because their brain's like, "Oh, we're falling? Okay. Okay. Hey, eyes, what are you doing?" And off they go. Okay? Instead of, well, the ears, I turn my head, my ears still say, "That way's down, we're good." Okay? But if you look any direction and your brain has become dependent on your eyes to tell you which way is up and down, and do this, it's like, we're going! And off they go. Okay? It's just really, really weird. It's also funny to watch them when they've gotten used to it, to being in zero gravity, what they do with objects. Yeah, they just do this and they expect that it's going to sit there because like for the last 6 months, that's what it did. Okay, and then it just falls, like coffee cups, markers, pens. Okay, yeah, it happened to Chris Hadfield. It happened to the commander of the international. He was giving an interview and he had a cup of coffee. He's like, "Yeah." And he just he crashed. And he just looked down. So yeah, it's pretty funny when it happens. All right, so this circle is then a delicate balance, or any circular motion is a delicate balance between that force and the desire to go in a straight line. They have to be balanced out. Okay. All right. So the figure clearly shows that in uniform circular motion, an object would fly off in a tangent if it was suddenly released, which is what I demonstrated when I almost hit Reese over there. Okay. So that object then, according to Newton's first law, moves in a straight line at a constant speed. Okay, but it would be equal to the speed it was moving in the circle at. Okay? It's just now that centripetal acceleration is gone. This is exactly how a sling works. Okay, so the David and Goliath story, okay, where he smoked Goliath with the rock from the sling. Okay, you can make a rock go way faster in a sling than you could ever hope to throw it. Okay, because you're whipping it around and around in a circle. Okay, and so basically you're lengthening the lever, okay, that's acting on it by having it in a sling that's longer than your arm, okay, and you're getting it going really, really fast. The trick is, where do you release it? I mean, I would have missed by a half a mile, okay, with my demonstration there, right? But if you're, using it all the time to kill wolves and bears and keep them away from your flock of sheep, okay, you get probably pretty accurate with the thing, okay, but it does get that rock moving really, really fast within the sling. I think I have a video about that too. Okay. Okay, so if we look at this example here, driving a car around a corner, all right, let's look at the effect that radius would have on our centripetal acceleration. All right, so we know that the formula for centripetal acceleration is v squared over r. Which corner, the small one or the wide one, should the acceleration be greater? The small one, okay, because r is smaller. So if we're looking at this and we got 28 squared divided by 320, okay, our centripetal acceleration on that corner okay, is 2.45 meters per second squared. That's about a quarter of a G. Okay? That means that if you weigh 200 pounds, you would feel a force of 50 pounds wanting to have you leave the circle. Okay? That's your buddy who takes the corner too fast, okay, and plasters your face up against the window. Okay? The force from the window pushing against your face would be equivalent to 1/4 of your actual weight. Okay? Does that sort of make sense? Now, if he takes the corner wider at the same speed, because he's still your crazy friend who wants to go fast, okay, so still at 28 meters per second, okay, we got v squared over r equals a. Now we've got 28 squared over 960. What did we do to the radius here? We made it bigger by a factor of what? 3, yeah. So what should my centripetal acceleration look like? 3 times less, yeah. Okay, that's 3 times less. If I multiply that by 3, it's 2.45. Okay, so taking the corner wider results in a smaller centripetal acceleration and thus a more comfortable turn, a safer turn, okay, because of that increased radius, taking the corner wider. All right. Okay, everybody good with that idea? All right, so that's what we just did for the math. Perfect. All right, so tomorrow we're going to go over some stuff to do with centripetal force. Okay, we have a shorter class and it's actually going to be split in half. We're going to have half of it before the Remembrance Day thing and the other half of it after. Okay, so remember there's a different bell schedule for tomorrow. It's posted on the school website. Okay, and then your test is Monday. Okay, so make sure you're getting ready for that. Okay.